We will now talk about geometric versions of Han-Banach. So geometric versions means we are talking about separation of convex sets by means of hyperplanes. What do we mean by a hyperplane? So this is a generalization of the notion of a straight line in the plane or a plane in R3 and so on. So what is a straight line? Ax plus by equal to c. This is a straight line in the plane R2. This can be written as f of xy equal to c, where f of xy is ax plus by, and that's a linear functional on R2. Similarly, a plane is ax plus by plus cz equal to d, and this can be written as f of xy equal to d, where f of xy is ax plus by plus cz, and that's again a linear functional in R3. Therefore, in general, we have let V be a real norm-linear space, and let so a hyperplane in V is a set f equals alpha, which is a short notation for set of all x in V. So set fx equals alpha, where f is a linear functional which is not identically 0. So alpha is a constant. So we are not talking about continuous linear functionals as yet. We are only saying a hyperplane is given by the constant sets of a linear functional. So we have the following proposition: a hyperplane f equal to alpha is continuous, is closed if and only if f is continuous. So proof. So one way is obvious. So if f continuous, then clearly set of all x such as fx equals alpha is a closed set. So f equals alpha is closed. So we want to now prove the converse. So normally assume f equals alpha is closed. So let us call this set as H. So H equals hyperplane f equals alpha. So this means that H complement is open, and since f is not identically 0, H complement is non-empty. Why? If alpha equal to 0, then there exists x naught such that f of x naught is not equal to 0. If alpha is not equal to 0, then 0, so x naught belongs to H complement. If alpha is not equal to 0, then 0 belongs to H complement. So in either case, you have that the hyperplane, the complement is a non-empty open set. Okay, so now we want to show that f is continuous. Okay, so let x naught belong to H complement. So f of x naught is not equal to alpha, so without loss of generality, we will assume that f of x naught is strictly less than alpha. Now H complement is open, so there exists a ball, center x naught and radius say 2r, which is completely contained in H complement. This is just the definition of openness. So we claim f of x is less than alpha for all x in Bx naught to R. So you have, the idea is this, so you have a ball, so you have x naught, and suppose I have x1, so f of x naught is less than alpha. Assume that f of x1 is bigger than alpha. Then you join these two. So we don't have the intermediate value theorem. If we had that, because f is not yet continuous, so in that case there would be a point where f of x would be equal to alpha. But instead we have something better, namely linearity and the convexity of the set, and therefore if you put t equals f of x naught minus alpha by f of x naught minus f of x1, then 0 will be less than t less than 1. Both these are negative terms, so the ratio is positive, and then this is bigger and therefore it is less than 1. Okay, so then if you put xt equal to tx1 plus 1 minus t x naught, then you have f of xt. This is just a simple calculation, is equal to alpha, and that of course is a contradiction because this entire line segment belongs to the ball and which is contained in H complement, and therefore you cannot have something which is equal to alpha. So now you take any z such that norm z is less than or equal to 1, and then you take f of x naught plus rz. The distance of this point from x naught is r, which is less than 2r, and therefore it belongs to the ball. So f of x naught plus rz is less than alpha. So implies for all such z, f of z is less than alpha minus f of x naught by r, and therefore unit ball, image of the unit ball is bounded, implies of course f is continuous. This was one of the various characterizations of continuity which we have seen. So a closed hyperplane means a level set or a set where f of x constant takes a constant value and f is a continuous linear function. Okay, so now we are going to prove as a proposition which is a very useful one. So let V be a real norm linear space and C contained in V a convex and open set. Let 0 belong to C. So for x in V, define P of x equals inf greater than 0 such that alpha inverse x belongs to C. So let us understand this definition. So C is a convex set and then 0 is a point in it, x is some vector in the space. So you take this line. So if alpha is very big, then alpha inverse x is very small, so its norm is close to 0, and 0 is an interior point in C. C is an open set and 0 is in it, and therefore when alpha becomes very big, alpha inverse x will be close to 0 and therefore will belong to C, and the bigger the alpha, the more it will be in C. So we are going to take the value, the infimum of all such alphas, namely just when alpha inverse x starts falling inside C. So this is called the Minkowski functional. attached to C, of course. Okay. So then 1, there exists an m greater than 0 such that Px is less than or equal to m times norm x for all x in C, x in B, sorry. And then of course, okay, 0 is also, that is obvious. And then C is set of all x in V such that Px is strictly less than 1. So this functional, Minkowski functional, characterizes the convex set. Then 3, for all x in V, for all alpha in R, we have P of alpha x is alpha times Px, and 4, for all xy in B, we have P of x plus y less than or equal to Px plus Py. Okay, so P is, so proof, P greater or equal to 0, obvious. Now C is open and 0 belongs to C. Therefore, there exists a ball, center origin and radius say 2r, which is completely contained in C. And therefore, if you take any x in V, you have x by norm x into R belongs to C. So this is one of the alpha inverses. R by norm x can be thought of as an alpha inverse such that alpha inverse x belongs to C, and therefore Px is the infimum of all such numbers. So this implies that Px is less than or equal to norm x by R for all x in V. So you can take 1 by R as m, and so this proves the first one. So now let us see the second one. So let x belong to C. So x is in C, so C is a convex set. So x is here, say 0 is also here. So if you take 0 to x, since C is open, therefore you will be able to extend this line a little more inside C itself. So this implies there exists an epsilon positive such that 1 plus epsilon of x is still in C. Therefore, by the definition of the Minkowski functional, Px is less than or equal to 1 by 1 plus epsilon, and that is strictly less than 1. Conversely, let us assume that Px is less than 1. Then what does it mean? Px is the infimum of all t or alpha or whatever you want, such that 1 by t of x belongs to C. So since that infimum is strictly less than 1, there exists a member of that set where you are taking the infimum which lies between these two numbers. So implies there exists a t which is still less than 1 such that 1 by tx belongs to C. Okay. So then C is convex and 0 belongs to C. Therefore, t times, so 1 by tx plus 1 minus t times 0, which is just x, belongs to C. So we have that, in fact, we have proved the second one, namely C is precisely the set. Now the third one is obvious, I won't bother about it, it's just straightforward right from the definition you have this. So let us now prove the last condition. Okay, so let xy belong to B. So by the definition of Px, 1 by Px plus epsilon, so epsilon is some arbitrary positive number, times x, this should belong to C. Similarly, 1 by Px plus epsilon times y, py plus epsilon will also belong to C. So now you take T equals px plus epsilon by px plus py plus 2 epsilon. Then 0 is less than T, which is less than 1, and C is convex. Therefore, T times 1 by px plus epsilon times x plus 1 minus T times 1 by py plus epsilon times y, and this, if you do the calculation, is nothing but 1 by px plus py plus 2 epsilon times x plus y, and this has to belong to C because of the convexity. So by the definition of the Minkowski functional, again, this means that p of x plus y is less than or equal to px plus py plus 2 epsilon. Epsilon is arbitrary, so this can go, and so you have proved this condition. Okay, so this proves all the properties of the Minkowski function. So we will now use this to prove a proposition. So V, a real norm-linear space, C, open convex set in V, and assume and x naught not an element in C. Then there exists a f in V star such that for all x in C, we have f of x is strictly less than f of x naught. So you have a convex set C, and your point x naught here, we are saying we can put a hyperplane which passes through x naught. So this is the hyperplane f equals f of x naught, and then C lies entirely to one side of this hyperplane. Okay, we can find such a hyperplane. So you know that in ax plus by equal to, if you take a line, it divides the plane into two regions. One is bigger than equal to C, bigger than C, and the other would be less than C. So similarly, a hyperplane divides the region like this, and C lies entirely to one side of this. Okay, so proof. So without loss of generality, we can assume 0 belongs to C. Why? Suppose 0 is not in C. Okay, I have to add here, this C is non-empty. That is very important, obviously. If C has to be non-empty, otherwise this theorem makes no sense. Okay, so therefore there exists some x1 belonging to C. So now you consider the set C minus x1. So what is this set of all x minus x1, x belonging to C? This is the algebraic difference, not set theoretic difference, but the algebraic difference. C minus x1 means set of all x minus x1, x belonging to C. Okay, so then x naught minus x1 does not belong to C minus x1, and 0 belongs to C minus x1. So we are in the previous situation, namely where 0 is in the convex set, and this C minus x1 is, you have just translated the origin, so the convex set remains convex. There is no change in that. Okay, so by the proof for this case, so there exists an f in V star such that for all x minus x1, x in C, we have f of x minus x1 is strictly less than f of x naught minus x1, and by linearity this means that f of x is strictly less than f of x naught. So there is no loss of generality in assuming that 0 belongs to C. Okay, so 0 belongs to C, and now we take W to be the span, one dimensional span of x naught. So what is that? So that is equal to set of all Tx naught such that T is in R. Okay, so now we define G W to R. So G of Tx naught equal to T. Okay, so this is for every T in R, and therefore this defines a linear functional on this. Okay, so now let T be positive. Okay, now 1 by T times Tx naught, which is x naught, is not in C. So by the definition of the Minkowski functional, T should be less than or equal to Px, P of Tx naught. Therefore, G of Tx naught is equal to T, which is less than or equal to P of Tx naught if T is positive. This is trivially true if T is negative, because T is negative, P is always non-negative, so this inequality will always hold. So this is true in fact for all T. And recall that P satisfies the conditions which we proved in the very first Hahn-Banach general version of the Hahn-Banach theorem, and therefore we get there exists an F from V to R linear extension of G and f of x less than or equal to P of x for all x. Now f of x is less than or equal to Px, which we know is less than m times norm x. This is also true for minus x, and therefore mod fx is less than or equal to m times norm x, and this implies f belongs to V star. So it's linear and it is continuous, therefore it belongs to V star. Then if x belongs to C, we have f of x is less than or equal to Px, and x is in C, so Px is strictly less than 1, and 1 is nothing but G of x naught, and because f is a linear extension, this is f of x naught. So for every x in C, f of x is strictly less than f of x naught, and this completes the proof. So we will now use this theorem to prove some separation theorems from convex sets. So when we have two convex sets, we will show that which are disjoint, we will show you can separate them by means of hyperplane, and sometimes under some other conditions you can actually strictly separate them. So what we have to measure this disjointness properly. Okay, so we will do that now.